I'm Siddharth Kaul and I welcome you to Edupedia world. Most of the time, it is required to measure the performance of the code or program that has been written or developed. Here in this video, I'm going to show how the performance of the program is measured in Matlab, how the code coverage is done, and what are the ways of improving the performance of the program. The video has been divided into 6 sections. First section is where I will provide overview for the measure of performance of program. Second section is where I will show how to use profiler and get profiling reports. Third section will cover code coverage in Matlab. Fourth section, I will discuss the ways to improve the performance of the code. In the fifth section, I will discuss the advantages of preallocation. The sixth and final section, I will emphasize on the use of vectorization of algorithm for better performance of code and program in Matlab. I will start this video by providing the overview of measuring performance, and I will introduce Matlab's timeIt function. The timeIt function and the stopwatch timer function, that is tick and talk, enable you to time how long your code takes to run. You can use the timeIt function for a rigorous measurement of function execution time. You can use tick and talk to estimate time for smaller portion of code that are not complete functions. First, let's talk about time function, that is timeIt. To measure the time required to run a function, you can use the timeIt function. The timeIt function calls the specified function multiple times and returns the median of the measurements. It takes a handle to the function to be measured and returns the typical execution time in seconds. Suppose that you have defined a function, compute function, that takes two inputs, x and y, that are defined in your workspace. You can compute the time to execute the function using timeIt. Here highlighted in bold are the lines that deals with the timeIt function. Here f is the handle to the myCompute function and I have passed the function handle to the timeIt function. This will return executed time in seconds. It is written something like this. F is equal to a handle to the myCompute function, and in the timeIt function I am going to pass this handle f. Now to estimate how long a portion of your program takes to run, or to compare the speed of different implementation of portions of a program, you can use the stopwatch timer function. These stopwatch functions are tick and talk. Invoking tick starts the timer and the next talk reads the elapsed time. It looks something like shown here. The code portion starts with tick indicating the start of timer and ends at talk and returns the elapsed time. So basically between this tick and talk, our program section or the code section comes whose time we want to measure. Sometimes program run too fast for tick and talk to provide any useful data. So if your code is faster than 1/10 second, consider measuring it running in a loop. Then average it to find time for a single run. Following are the few tips you can follow when measuring the performance of your code or your program. The first thing is to time a significant enough portion of code. Ideally, the code that you are timing or the program that you are timing should take more than 1/10 of a second to run. Then only it makes sense to measure the time. Second is put the code you are trying to time into function instead of timing it at the command line or inside a script. Timing it in a function makes it convenient and easy for you to understand, and you can take average or median of various measurements. Third, unless you are trying to measure first time cost, it's better to run your code multiple times. So use the timeIt function for it. The timeIt function will run your function multiple times and it will give you a median of your measurements. Fourth one is to avoid clear all when measuring the performance. So whatever the code you are measuring the performance for, you should avoid commands like CLC, clear all, that clears the workspace or clears the memory or deletes the memory, because it takes time to perform this action and it will show an impact in the performance of your code. Then the last one is to assign your output to a variable instead of letting it default to answer. As writing over and over on answer variable, the Matlab takes certain amount of time that is adds to the timing of your code. So to improve performance, it is better to output your value or your answer to a variable instead of the default answer variable. Moving on to the second section. In this second section, I will show you how to use Profiler and get reports from it. So the first question that comes into your mind is, what is profiling? Profiling is a way to measure where a program spends time. After you identify which functions are consuming the most time, you can evaluate them for possible performance improvement. Also, you can profile your code as a debugging tool. For example, determining which lines of code MATLAB does not run can help you develop test cases that exercise that code or make that untouched portion of code to execute. If you get an error in the file when profiling, you can see what ran and what did not to help you isolate the problem. You can profile your code using the MATLAB profiler. The profiler is a user interface based on the results returned by the profile function. There are certain general processes that are involved in any kind of profiling, either on MATLAB, either on C, either on Python, and whatever. So first you run the profiler on your code. Second, in the profile summary report, you look for functions that are using a significant amount of time and are called most frequently. Then you view the profile detail report for those functions and look for the lines of code that take the most time and are called most often. Consider keeping the copy of the first detailed report as basis for comparison. So based on this, whatever changes you do in your code, that will be your benchmark. Like you have to be faster than this first base report. Then fourth is to determine whether these changes you make to those line of code can actually have an impact on the performance. Say for example, if you have a load statement within a loop, you might be able to move the load statement outside the loop. So this way it will not be loaded each and every time the loop executes. So it will be loaded only once. This may improve the performance. Then fifth is to implement the potential performance improvements in your code. So you did the changes, you took the load function out of the loop, you took other functions out of the loop, you made it run only once, you made the performance changes and you save your code. Then you run the profiler again and compare the results to the baseline that you set. So if you profile the identical code twice, you may get slightly different result each time. This may happen because of inherent time fluctuation that are not dependent on your code. So to continue improving the performance of your code, you need to repeat these steps over and over again till you reach to an optimum level that is satisfying to you or satisfying to your program. To show one of the ways to work with the profiler. So the profiler can be opened by typing the command profile viewer in the command window. A small profile window will open where it will show a profile summary. It will have a start profiling button. It will have a bar that says run this code and it will have a profile timer. So let me run an example. Let me take an example of Lotka-Volterra equation. So it is basically an inbuilt equation available in the MATLAB. So this equation is known as a predator-prey equation. That is a pair of first order nonlinear differential equation that is frequently used to describe the dynamics of biological systems in which two different quantities, that is predator and prey, interact and how they will grow and all that stuff. You can get to know more about this by doing a simple Wikipedia search. So I'm going to do, using the ODE23 solver, I'm going to invoke the Lotka-Volterra equation. I'm going to pass 0 to 2, that is time, and then I'm going to do 20, 20. So let me profile this simple line of code. So when I start the profile and stop the profile, it runs through the code and it takes it almost took 0.257 seconds to run this equation. So it generates a summary like this. We will see into this summary now. Profiler at the end of profiling generates a profile summary report. This report presents statistics about the overall execution of the function and provides summary statistics for each function call. Let's talk about what I demonstrated in the demo video, the Lotka-Volterra model. In the summary, you will see multiple columns. In the function name column, you will see the list of all the functions called by the profiled code. The functions in the report appear in order of the time they took to process. Then you will see a column titled calls. This shows the number of times the profile code called given function. Then you will see a column titled total time. This obviously represents total time spent in a function, and this includes all access child function through the function and the unit of the measurement is in seconds. As I said before, this time is inclusive for time spent in the child functions. The profiler itself takes some time, which is included in this self time column. The total time can be 0 for files whose runtime is inconsequential. Then you will see a column named self time. Total time in seconds spent in a function excluding time spent in any child function. Self time also includes some overhead resulting from the process of profiling and some lag that profiler happens, that is also included in this. Then you will see a total time plot. It is a graphic display showing self time compared with total time. Moving on to the third section. In this third section, I will show how to use profiler to determine the code coverage of your program. Basically, in my current directory folder, I have a file that is called samplescript.m. I'm going to try and get a code coverage report for this file. So first, I'm going to open my profiler. So I'm going to type profile viewer. In the run this code, I'm going to, as my current folder path is already set to this and my file already exists in the current folder. So I'm just simply going to call back my script file like this. So I'm going to call samplescript.m and I'm going to start the profiling. The code runs, something runs in the background and it gives me a profile summary like this. So it says that total time taken was 0.205 and for total time versus self time, all those plots are generated here. Now I will close this window for now. In my current folder path, I'm going to go into this settings, into this actions looking tab. I'm going to click on it, and in the report section, I'm going to open the coverage report. So a new window opens that shows the profile coverage, that is a profiler coverage report that will show like the coverage of the script that has been executed. So my sample script.m, the coverage shown is 100%, the total time taken is 0.2 seconds. So the file can be opened by left clicking on it and the file will be opened in the MATLAB editor. So this is how you can generate code coverage reports for any of your MATLAB script files and function files. In this fourth section, I will show the techniques to be used to improve the performance of your code. There are certain programming practices in MATLAB that one can follow to improve the performance of the code. The first is to pre-allocate. This is something that instead of making MATLAB resize arrays continuously, pre-allocating certain maximum amount of space for an array helps MATLAB to execute the code faster. I will give a little detail on this in coming section in the video. Second is to vectorize. MATLAB being a matrix and vector based tools, so it makes sense that you write the algorithm as a form of vector instead of a loop based. So obviously writing the algorithm in form of vector will improve the performance of the MATLAB program. We will see into this as well. Third is to avoid redundant computation. So it is better to put section of code that does not evaluate differently with each call outside the looping section. Let's take the best example of this is loading a file. So loading a file can only be done once and the operation on the file can be done many times. So it makes no sense to call the loading function every time in a loop. That's why we keep the loading function outside the loop and then multiple times we operate on the function. Fourth is to use different variables or to create new variables and assigning a data of different data type to your existing variable. This is done because changing the class or array shape or data type takes some extra amount of time. So changing data type from integer to double will take some extra amount of time, or downsizing from character string to character or to integer will take some extra amount of time. So to shave off that time, it is better to use a different variable or to create a new variable to allot those values. Fifth is to use more of a short circuit parameters like and operator or operator. This is because MATLAB evaluates the second operator of the short circuit parameters only when necessary. So only when the result is not fully determined by the first operand that the MATLAB performs the second operand. Sixth is to avoid global variables. Global variables is a big no-no. Minimizing the use of global variables is a very good programming practice, and global variables are known to slow and decrease performance of the code. This is known among all the languages. Seventh is to avoid overloading built-in functions or any standard MATLAB data classes. Eighth is to avoid using data as code. So let me give you an example here. Suppose you have a large portion of code that generate variables with constant values. It is better to construct the variables and save them in a mat file and load them instead of regenerating it again and again. These are certain ways or techniques you can use to improve the performance of your code. In this fifth section, I will be emphasizing on using pre-allocated arrays and structures. Basically, the looping statements in MATLAB, that is the for and while loop that really increases the size of data structure each time through the loop, adversely affects the performance and the memory usage. This is because repeated resizing requires MATLAB to often spend extra time looking for larger continuous blocks of memory and then moving the array into these blocks. So to avoid such scenarios, you can save time by pre-allocating the maximum amount of space that can be required for the array. Here in this slide, using the tick and talk, I have shown the difference between the performance by pre-allocating size and by not pre-allocating size. On the left, you can see the code section where the pre-allocation has not been done. So this is for a size of 1 million. The time it takes is close to 0.3 seconds. On the right, you can see the same code section, but here I have already defined the size to be 1 million. The drastic change in performance can be seen from the elapsed time, which is around 0.01 seconds in this case. So as you can see, pre-allocation helps, and it helps a lot. The next thing I'm going to talk about is vectorization and how it can speed up our program. Again and again, it has been emphasized that MATLAB is a matrix laboratory. Every operation in MATLAB is basically a matrix. MATLAB is optimized for operations that involves matrices and vectors. The process of revising loop-based scalar-oriented code to use MATLAB matrix and vector operation is called vectorization. This is worthwhile for the following reasons. First off, it's the appearance or the way the code looks. The vectorized mathematical code looks more like the mathematical expression found in the textbooks, making code easier to understand. Second, it is less error prone. As loops are eliminated, the chances of errors are reduced and the code size is often reduced. So by law, fewer the number of code lines, the fewer the chances of errors. Third and the last is the performance. Vectorized code often runs much faster than the corresponding code containing the loops. So these are the reasons where vectorizing your code is some worthwhile effort. Let me show you a couple of examples of what vectorization really is. On the left, in the red box, you can see a simple code snippet that computes the sign of 1001 values ranging from 0 to 10. The snippet has a for loop that iterates over 0 to 10 and then a statement that computes the sign for each iteration. This code snippet can be vectorized as shown in the green box on the right. Here I have defined a vector t from 0 to 10 with a division of 0.01. Then as MATLAB supports matrix computation, I call the sign function and pass the complete vector t to it, getting in return the matrix y that contains sign of each of the element of t. This vectorized code is more efficient use of MATLAB and will definitely run faster than its looping counterpart. Let's take another example. Here in the red box, I have a code that computes the cumulative sum of a vector at every fifth element. For that, the code snippet has to go through the procedure of defining the size of array y by calculating the size from the original length x. The more efficient way or the more concise way I have duplicated this is in green box. Just by doing cumulative sum of entire x vector, and then I am passing only the fifth element to the vector y. So this is also one way of accomplishing the same task. So instead of segregating it, cumulative sum each and every element, and then I separated only the fifth element that we need. Array operations. Array operations are something that is the best example of vectorization in MATLAB. For repetitive operations on each of the elements in an array operations are used. For example, say you have information of diameter and height for one cone. You can easily calculate the volume using the formula V is equal to 1 by 12 pi d square into h. Now, if you happen to collect information on 10,000 cones, then both D and H will become vectors with 10,000 elements in each of them. And you have the ability to calculate volume for each of these 10,000 elements. In most programming languages, when doing this, the code will look something similar to shown here in the slide. So there will be a for loop, and inside the loop there will be an equation calculating volume for each of the elements. But with MATLAB, you can perform this whole loop in a single statement by vectorizing the code. You can just write in the formula and use the multiplication operator, that is the dot star and dot to the power, to make the MATLAB aware to do operation on each element, and voila, you will have the vector volume with all the calculated volumes. So basically V will become a vector of 10,000 elements that are the volumes of 10,000 cones. Logical array operation are another sort of operation that can be done in bulk, as I demonstrated in the previous slide. So apart from these arithmetic operations, logical operations also have these capabilities of bulk operation. MATLAB comparison operator accept the vector inputs and return vector outputs. For example, suppose while collecting data from 10,000 cones, you record several negative values for the diameter. That is actually not possible. You can determine which values in the vector are valid by a simple greater than and equal to operator. So by just writing in MATLAB vector d as greater than equal to 0, the MATLAB will return a logical vector with 1 at places where it is true and 0 at places where it is false. So you in turn can use this to index the actual v vector to separate the good values from the bad. So you can create another vector v good that are consist of only the good values by logically indexing vector v. Matrix operations. Matrix operations in MATLAB are the linear algebraic form of calculation. These are the most useful in vectorization when working with multi-dimensional data. Suppose you want to evaluate a function f of two variables x and y. The function is x to the power minus x square minus y square. To evaluate this function at every combination of points in the x and y, you need to define a grid of values. Let's take x from minus 2 to 2 and y from minus 1.5 to 1.5. Now to do that without vectorization, it would require to write two loops to iterate through each of the vector combination. But here, using either the mesh grid or ND grid, we can achieve the same result in a single statement. The point to remember is that mesh grid is only good till 3-dimension matrices. For higher dimensional matrices, the ND grid function needs to be used. So let me show you an example here. So to create a grid of x and y from x ranging from minus 2 to 2 and y from minus 1.5 to plus 1.5, I just called the mesh grid function and passed these x and y. So in the return, I got the ranges of x and capital X and capital Y. Now I will put this in our equation, that is x to the power minus x square and minus y square, and I will evaluate the complete function over the whole grid of values.
Here in the slide, I have summarized some commonly used function in vectorization. There is a all function that determines if all array elements are non-zero or true. Then there is any function that determines if any array elements are non-zero. Then there is cumulative sum, that is sum that does the cumulative sum. Then there is diff that does the difference and also does approximation of derivatives. Then using find function, indices and values of non-zero elements are discovered in a vector. Then there is something called index to script that, as the name suggests, find the scripts from the linear index. Then there is ipermute that does the inverse permute of n-dimensional array. Then there is logical function is used to convert numerical values to the logical data type. Then there is a mesh grid that generates a rectangular 2-dimensional or a 3-dimensional grid from the input values of x and y. Then similar to mesh grid, there is ND grid that generates rectangular grid for any n dimension. It is not limited like mesh grid for only 3-dimensional or 2-dimensional array. We can go up to 4th dimension, 5th dimension and so on. Then permute function is used to rearrange dimension of n-dimensional array. The prod function does find the product of array elements. Then there is a repeat matrix function that repeats the copies of inputted array and creates new arrays from the copies of its input. Then there is a reshape function that reshapes the array and changes its dimension. Then there is a sort array function that sorts the elements in a vector. Then there is squeeze function that removes the singleton dimensions. Then at last there is subscripts to linear indices. For those who don't know what subscripts are, so basically in a multi-dimensional array, when you point to an element like third row, second column, that element you want, you are saying that the subscript for that element is 3, 2. For the linear indices, it can be some nth number element from the start. So these conversion function converts these subscript to linear indices and then help with array addressing. One of the example I would like to show is a function called repeat matrices or repmat. When vectorizing code, you often need to construct a matrix with particular size or structure. As shown on the commands on the right, you can create a 5 by 5 matrix of uniform values of 10 by using the function once, using the function 1 to generate the 5 by 5 matrix and then multiply it by 10. Other case can be that you might require a matrix with repeating value. Here using the repeating matrix function, we can have a vector v in this case from 1 to 5 repeated 3 times for 3 rows and 1 time for a single row. So we get a 3 by 5 size array where the first row is 1, 2, 3, 4, 5, second is 1, 2, 3, 4, 5 and the third is 1, 2, 3, 4, 5. On the left, I have demonstrated the capability of repeat matrix function to build matrices using the smaller matrices or vectors. For A in repeat matrix function, I provided the repeating sequence as a vector from 1 to 3 that is repeated in 5 rows 2 times in each row, creating a 5 by 6 matrix. Similarly, in B, in the repeat matrix function, I have provided with a 2 by 2 matrix that is repeated 2 times vertically and 2 times horizontally, creating a 4 by 4 square matrix. This is how using repeat matrices we can construct matrices. There are a number of ways in which you can find the redundant elements of a vector. I will be showing one of them here that involves using the function diff. So concept is, after sorting the vector elements, equal adjacent elements will produce a 0 entry when you use the diff on that vector. But as diff function produces a vector that has one fewer elements than original vector x, you must add an element that is not equal to any other element. So nan or not a number will always satisfy this condition. Now after this, you can use logical indexing to choose a unique element in the set. The code for the same is shown here. I have vector x with repeating values and the aim is to find only the unique elements. So first, using the sort function, I will sort the vector and then using the diff function, the repeated elements are made 0 and then I replace those repeated elements with not a number. Then whatever elements that are not equal to 0 are identified and are considered as the unique elements. The same thing can be done using the unique function available in the Matlab, but the function provides more information than needed and will slow down the execution of the code. So you can check out both of them. Counting elements in a vector. There are multiple ways in which you can count the occurrence of an element in a vector. Let's say I have a vector x. This vector x is shown here in the slide. After I sort this vector, I can use the find function to determine the indices of 0 values in difference of x and to show where the elements have changed the value. So what this will do is that the difference between the subsequent indices from the find function will help me identify the number of occurrences for a particular element. The find function does not return indices for not a number elements. So basically you can count the number of nan in infinite values using the isnan and isinf functions. So that are performed in the last 2 lines of this code snippet. This concludes our video program performance in Matlab. In the next video, we are going to take a theoretical look into memory usage in Matlab, like what goes on behind the scenes. So until then, please subscribe and thanks for watching.